Welcome back to Part B of exam number 1 review session. We now have a block diagram that's consistent with our difference equation, and this piece right here is feeding that delay block, and the output of that comes out of that delay block, and then we have this piece feeding or giving us those two waveforms, and that piece right there is all of that, if that makes any sense. So that now I can label this as x1 of n, and this is x sub 2 of n, to produce a state space representation from that difference equation. If this right-hand signal is x sub 1 of n, this is x sub 1 of n plus 1, and this is x sub 2 of n plus 1. And I can now create my state space representation. X sub 1 of n plus 1, x sub 2 of n plus 1. I now need to be a linear combination of my states, x1 of n and x sub 2 of n, and the input u of n. What's x sub 1 of n plus 1? What creates that? X sub 1 of n plus 1 is the output of that rightmost summing junction, and what signals come in to create that, or to produce that. I have 3 signals to make that. The first one is from the bottom. That's 1.4 times y of n, but y of n is x1 of n, so I should be able to find that by saying there's 1.4, x sub 1 of n. Plus the signal coming in horizontally from the left, which is x sub 2 of n, and I can pick that up in my state space representation with a 1. And do I have anything else? I have a third signal coming in from the top, and that's a scaled version of my input, u of n, scaled by 1, or now I have a 1 times u of n. That's now my expression for, or equation for, x sub 1 of n plus 1, x sub 2 of n plus 1. How do I fill in these 3 blanks? Do I have anything that scales x sub 1 of n? It's now the minus 0.45. Is x sub 2 of n used to build or create x sub 2 of n plus 1? No. So I have 0 here. And does u of n come into play to make part of x sub 2 of n plus 1? It's coming in with a 1. What's my output equation look like? In this case, I now have defined a phi matrix, that's my system matrix, and a gamma matrix, my input matrix. What's the output equation look like? Y of n is equal to something times x1 of n, x sub 2 of n, plus something times u of n. How do I fill in these blanks? Does y of n have a direct connection from u of n? Does the input directly come in to make y of n? No. So there's nothing in the direct feed-through matrix. How do I express y of n in terms of x1 of n and x sub 2 of n? It's just x sub 1 of n and no x sub 2. And this now gives me my output matrix H and my direct feed-through matrix J. So there's another way to build. I apologize, it got broke because I went into the cloud, and so that seemed to have problems. But I now have another way of finding a state space representation from a difference equation that contains delayed inputs. Is this system stable? And how would I determine stability of this system? I need to find the eigenvalues of what? I need to make it the eigenvalues of my system matrix, which is the phi matrix, the capital Phi matrix. I need to find the eigenvalues of that. How many eigenvalues or poles do I have in this system? It's a second order system, so I actually am looking for 2 poles. The eigenvalues of phi I can find by looking at the determinant of lambda I minus phi and setting that equal to 0 and finding the values of lambda that cause that to be true, or for that to equal 0. In my case, I have the identity matrix is a 2 by 2 matrix multiplied by lambda, and I subtract the phi matrix, and a 2 by 2, you should be able to find the determinant of that. That's the product of the diagonals minus the product of the off diagonals. Or I now have lambda squared minus 1.4 lambda plus 0.45. And do you see how to factor that? 5 and 9, or 0.9 and 0.5, will give us 5 and 9 is 45, and 0.5 and 0.9 give me 1.4, so this actually factors into lambda minus 0.9 and lambda minus 0.5. You could, if you didn't see it, you don't have to see it, just plug it into the quadratic formula, and it could give you complex roots, depending on what that quadratic equals. So now I have roots or eigenvalues at values of lambda that cause those factors to become 0 or to vanish. I have eigenvalues at 1/2 and 0.9, or those are the poles of my system. What can you tell me about the magnitude of those poles? Those are complex, they're all real, they have no imaginary part, but I can now find the magnitude of those complex numbers. Where are they relative to the unit circle? They're all inside. And what does that tell me I can conclude about stability or not of my system? Now my system is stable. So if we didn't know it before, from that particular difference equation, we can now say, oh, that difference equation actually produces a stable system. What's the settling time? Or maybe I should say, which root is dominant? I have 2 poles, and you should be able to visualize those in the complex S-plane as 2 x's. One's at 1/2 and one's at 0.9. You said they're stable, they're all inside the unit circle. What are the dominant poles? Or which one's dominant? It's the one that's closest to z equal to 1, that's the one at 0.9. So what? That now allows us to use that one in our calculation of settling time. Our settling time now can come from this y of n equaling 1% of where we started, and that's also the r, the dominant r, raised to the capital N times y of 0. That gives us y of capital N. Or these cancel, and we can solve for, we're trying to solve for capital N. We see that capital N in this case, capital R in this case is 0.9 raised to the N, and we need that to be 0.01, or what value of N causes that to happen. And if you needed to, you could just keep going with raising 0.9 to higher and higher powers until it gets less than 0.01. But since we know logarithms, we can now solve for N. And that says that N, if we take the log base 10 of 0.01, which is 10 to the minus 2, that's minus 2, so that N is now minus 2 log base 10 of R, which was the 0.9, and that ends up being 43. Log of 0.9 is minus 0.04 something, so that's quite a few sample periods before you settle. 43. What's the transfer function? Do we always use that equation for settling time? The answer is yes. We will just identify what do we use for R? What if we did have complex poles? What would we use for R? We would use the magnitude. We would find the R that's closest to 1 and just use that. That's what we're going to agree on in this class. So there's the system stable. We could find it by the eigenvalues, or if you wanted to, if you didn't like doing linear algebra, you could say, let me find the transfer function and find the poles of the system, right? So what's the transfer function? Well, we could do the z transform of the difference equation. To give us that from our difference equation. We can factor out the y of z. We have 1 minus 1.4 z to the minus 1 plus 0.45 z to the minus 2 equaling z to the minus 1 plus z to the minus 2 u of z. Or y of z over u of z is now our transfer function g of z, which is z to the minus 1 plus z to the minus 2 over 1 minus 1.4 z to the minus 1 plus 0.45 z to the minus 2. And we could multiply that by z squared over z squared, 1, to get things in a positive exponent on z. And now if we wanted the poles of that transfer function, that would just be the roots of the denominator. And that's the same equation that we had before. And we've simply verified our results with the eigenvalue that we had with the eigenvalues. What if we started with this transfer or these state space representations and wanted to get the transfer function. If I didn't give you the difference equation, now if I gave you this and said give me the transfer function, what's the transfer function? Do we know how to find that? I'm going to assume that you can do that and just get the g of z. Is that okay, since we're running short of time? What about if I ask the following? What if I gave you an input u of n that was 0.7 to the n cosine of pi over 8n for n non-negative, and I said, what is the structure of the output? How do I find that? So now this is the same system, the difference equation or the state space or the block diagram or the transfer function, and I say, here's the input that I'm applying to the system, and I want you to tell me what's the structure of y of n. Now I don't need to know the exact answer, I just need to know the terms that make up the structure. What do I need to find in order to find the structure of y of n? R? Which R? Now I can't hear. Yes. So now, what does this waveform look like? What is this waveform? Is it a sinusoid? Is it always on? This is an exponentially damped cosine, isn't it? So it's contracting because 0.7, the R for this, is shrinking. It's less than 1. So this is an exponentially damped cosine. And that's what I'm exciting my system with. But if I just walked up to the system and kicked it, how would it respond? Can you tell me, based on what we've already done earlier? If I just walked up to the system and kicked it, or initialized some initial values, how would it respond without an input? Based on what's on the screen, can you tell me? These are some R's, are they not? We have an R at 1/2 and we have an R at 0.9. That's how this naturally wants to respond to two initial conditions, is to decay at 1/2 and to decay at 0.9. That's the homogeneous solution, or the natural solution. That's the y sub h. Then we're also introducing some additional structure from the particular input, right? The particular input is this decaying, exponentially decaying sinusoid. So we put those two pieces together, and that gives us our structure of y of n. So if I'm asking for the structure, you want to find the homogeneous piece. That's the natural behavior. And you just told me that that comes from the poles of the system, the transfer function, which are at 1/2 and 0.9. If somebody said, what's the natural response of the system, you could say that once you have the poles. That tells you how your system naturally wants to move. And it's stable, isn't it? An initial condition will decay. What about the particular structure? That's what results from the particular input, or the response due to the forcing function or functions. So that the particular solution is now going to be beta 1, 0.7 to the n cosine of pi over 8n. And if we shake a system at that, with that excitation, we could also get the sine piece. So we now say plus beta sub 2, 0.7 to the n sine. And for the structure, it's the combination of those two pieces, the homogeneous or natural and the particular. The structure now, and I will put some new coefficients because they may differ from just the homogeneous or just the particular. Now I have alpha 1, 0.5 to the n, plus alpha sub 2 bar, 0.9 to the n, plus beta 1 bar, 0.7 to the n, cosine pi over 8n, plus beta sub 2 bar, 0.7 to the n sine. And that's the structure. Or you could combine the sine and the cosine into a phase-shifted cosine or a phase-shifted sine. That's equivalent. What if I gave you the following? So I'm now, say, given a pole zero diagram I should be finishing up shortly. I apologize. Oh my, maybe a couple hours, okay? We'll be finishing up in a couple of hours. 3 a.m., I've got plenty of time. Sure. 7 hours, right? All right, given a pole zero diagram for, let's say, a waveform, capital X of Z, what is the structure of little x of n? Meaning, suppose that I now give you a z-plane, and I now put some poles and zeros down. Maybe I put some poles here that are at 0.75 plus j 0.25. Let's say this one's at 0.5. We have a 0 at 0.25 and a 0 at the origin. And this is 0.75 minus j 0.25. What's the structure of my response? Little x of n. What's x of n look like structurally in the time domain? Can you tell me from this given information? And I'm going to assume that my region of convergence is unbounded. So this is for a right-sided. But let's not worry about that. I just want the structure. Can you tell me from this pole zero diagram of capital X of Z what the structure would be? Or can you even create what capital X of Z looks like as a pole zero expression? Can you give me the poles and zeros in a transfer function? And I hope the answer is yes. You now could say capital X of Z. Maybe I don't know what the gain is. I'll say that's alpha. Do I have any zeros? I have one at the origin, so that's one of my factors in the numerator. What's my other factor? It vanishes when the 0 is 0.25. How many pole factors do I have? One is there. Where's the other one? And here's the sort of the explicit way of factoring those complex conjugate pole pairs. We have the real part, and we have the imaginary part. And that's the factor of my complex poles. Given this, can you tell me the structure of little n? What does little n look like structurally? What are its modes? How does it move if you simply excite it? Do the zeros matter on the structure? Do the location of your zeros influence the structure of your response? No, it's only the poles. What's that real pole give you in terms of a structure? A decaying exponential. And what's the factor? It's something less than 1, isn't it? And it's really just the location of that pole. So this real pole at 0.5 gives us that piece of the structure of little x of n. What's that complex pole give us? When you see complex poles, what should you be thinking? Sinusoids, what kinds of sinusoids? They're now, where are they relative? If they were right on the unit circle, would they be collapsing or expanding? They wouldn't be, would they? They would just be sitting there shaking at the appropriate frequency. But what's this one doing? Where is it located? It's inside the unit circle, so it's collapsing. And it's collapsing now at a particular value. And how do we find the value that it's collapsing? Now we would actually need to find the polar form description of those rectangular numbers. So we would need this radius and that angle. The radius tells us how quickly they collapse, and the angle tells us how it will move around in a sinusoidal pattern. So once you're given these complex poles, you can now say, oh, I know that that's now beta 1 r to the n cosine of theta to the n plus beta sub 2 r to the n sine of theta n. And I said, let's go ahead and let this be right-sided, or have our region of convergence outside, where r is now this square root of the sum of the squares. It's the hypotenuse of that right triangle from those poles. This would actually be 0.7902, and theta is the inverse tangent of 0.25 over 0.75. And that ends up being, in degrees, 18.43 degrees. You can tell a lot by just looking at the transfer function or the expression for capital X of z. Question? Yes, the question was, if we had another set of poles, let's say that they are right here and here, they would give rise to another set of decaying exponentially damped sine and cosine, where the damping would be influenced by r sub 2, and the angle in their argument would be theta sub 2. So if somebody locates those, or if they're existing in your transfer function, you just need to find their polar form, and that gives you the decay and the angle in the argument. That's enough, isn't it? Stick a fork in it, we're done.